a session page of the symposium website. I shall share my screen so that you can see the posters that the speakers are talking about, as I did last week, for anyone who wasn't connected last week, and we'll give the speakers their 3 minutes. Our first speaker is Dimitri, and he's going to tell us about his poster on pneumatic superconductivity, orbital antiferromagnetism, normal state pneumacity, and density waves in twisted bilayer graphene. Dimitri, if you just give me 1 moment to bring up my second screen. Can you confirm that you can see my screen, Dimitri?
Yes, I do.
Fantastic. Okay, so the floor is all yours. Please tell us why we should come and have a look at your poster. I'll give you 3 minutes.
All right, thank you. So I work with Laura Klassen and Andrei Chubukov at the University of Minnesota. And this poster is a compilation of our 2 papers on twisted bilayer graphene. So in our work, we were interested in electronic instabilities in twisted bilayer graphene, and we were studying it within the weak coupling approach. So in the left column of the poster, I show the model which we're studying. It is essentially a model which has 2 features relevant for twisted bilayer graphene. And these features are van Hove singularities, so the presence of van Hove singularities, and the presence of non-local interactions, which were already mentioned today. So we study an effective patch model. We say that we only restrict fermions to live near these van Hove points because these points have the main contribution to physics. We show that there can be either 6 or 12 van Hove singularities. And then using these non-local interactions, which we particularly took from a paper by Kang and Vafik, we introduce a set of couplings to study just a simplistic but nevertheless interesting model. So in the 2 columns, in the middle and the right one, we study instabilities. So middle column is an instability in particle-particle channel. So it's superconducting instability. We studied both 6 and 12 patch models. And what we have shown is that non-local interactions can give rise to superconductivity already at the bare level of couplings, so without renormalizations due to high energy fermions. We also have shown that in the 12 patch case, the situation is even more interesting because there are 2 attractive superconducting channels which couple in a non-trivial way, and their coupling results in a ground state which breaks rotational symmetry, so realizes a pneumatic superconducting state. In terms of theory, it happens because of the unusual term in the free energy functional. And finally, the right column is a discussion of particle-hole instabilities. So what we have shown is that due to these non-local interactions, there are a lot of instabilities in different channels. However, the main instability is the orbital antiferromagnetic instability. So it's an instability where there is ferromagnetism within one orbital, but between 2 orbitals, the order is anti-parallel, so antiferromagnetic. And this state is exactly the same which was obtained in the strong coupling analysis by Cunning-Vafik and a few other groups. So we also observe attraction in pneumatic channels, which doesn't happen for just standard Hubbard interactions. So this is a particular feature of non-local terms. And the presence of this attraction implies that there are at least strong pneumatic fluctuations or even potential pneumatic order. So there are 2 references to our papers in this poster, and I encourage you to take a look at that. And there will be also a talk by Rafael Fernandez tomorrow related to pneumaticity. Thank you.
Fantastic. Thank you very much, Dimitri. I shall stop sharing my screen. I've put a link into the group chat to Dimitri's poster. Our next poster presenter is Emil. And I shall also now put a link to the poster in the group chat. And bring the poster up onto screen. Emil, you have 3 minutes now to tell us why we should come and have a look at your poster. Can you hear me?
Yeah.
Fantastic. The floor is yours.
Good morning and evening, everybody. My name is Emil Anneblink, and I'm a PhD student at the University of Illinois, and I'm advised by Professors Harley Johnson and Professor Elif Ertekin. So in many of the talks last week and this morning, we have seen some beautiful experimental images of Moiré superlattices. This morning we heard from Ava, and last week we heard from Jim Hone, Paco Gunet, and Dmitry Basov on how strain alters the superlattices that we see, and also the emergent electronic properties. However, we've also heard how easy it is to have non-uniform strain, and importantly, the absence of methods to control that strain field that results. The primary motivation of our work is to be able to develop a method to control the electronic properties by focusing on how to control that superlattice structure. We do this by understanding Moiré superlattices through a dislocation framework. We build on dislocation theory that has been developed for bulk materials and work that is pioneered in the 2D material space by Dye and Srolovitz, Zhang and Tadmore, Pochet and Johnson, and then Chen and Shan. And for this work specifically, we focus on the dislocation structure and relaxation in bilayer graphene. The first step of our analysis is to identify dislocations in Moiré superlattices from the atomic definition of dislocations. Here in the central panel, you can see that we use a diagram that presents the bilayer graphene topology similar to that of Pablo Herrero, where we understand the Moiré topology starting first from full dislocations, and that progresses, and the full dislocations separate boundaries between regions of identical stacking for graphene that's AB and AB stacking. The two atom basis, however, means that the full dislocations can split into partial dislocations that separate equivalent stacking locations. So for bilayer graphene, that's separating AB and BA stacking locations. Finally, the partial dislocations rearrange along the triangular symmetry of graphene to reproduce the topology of the Moiré superlattice we're familiar with. And this is all seen in the central panel. We use this topology to look both at stretch Moiré patterns, similar to what Ava discussed this morning, as well as twist Moiré patterns that are more identical or more similar to what the bulk of the bilayer graphene work has been done on. Stretch Moiré pattern superlattices are arrays of partial edge dislocations where the Burgers vector and line directions are 90 degrees from each other, while twist superlattices are screw dislocations where the Burgers vector and line dislocations are parallel. So if you have any questions on this work, please drop a reply on my poster or email me. Thank you.
Thank you very much, Emil. The next poster presenter today is En-Min Shi. I shall put a link to the poster up now onto the group chat. En-Min Shi, can you hear me?
Yes.
Good. Let me bring your poster up on screen, and I'll reload the clock and give you 3 minutes to tell us why we should come and have a look at your poster.
Thanks.
So please, the floor is all yours.
Hi, everyone. My name is En-Min Shi. I'm from Corey Ding's group from Columbia University. And in this poster, we report the study of twist bilayer tungsten diselenide with transport measurements. Tungsten diselenide is a semiconductor with parabolic band and a large band gap. When exposed to a Moiré potential generated by misorientation of lattice, the parabolic band will be cut off from top. So the bandwidth can be changed continuously by decreasing the twist angle, and we can tune the Coulomb interaction to kinetic energy ratio from weak to strong Copley regime. And indeed, in this work, we observe correlation effect from this tunable flat band for devices with twist angle smaller than 6 degrees. We observe insulating peak from half filling of the Moiré band, which is not predicted from the single particle picture, as shown at the left bottom of the panel. And on the top right upper of the panel, we can find that the insulating state is sensitive to the displacement field, or radical electric field. We can change the insulating peak strength by varying the displacement field and have a metal insulating transition at lower or higher critical displacement field values. The reason is that the flat band structure can be tuned by the displacement field. The Van Hoff singularity point will move across a band as the displacement field is changing. And when it is located at half filling, the insulating peak is the strongest. This shows that the system in twist angle between 4 to 5 degrees is not in strong coupling regime, where the insulating state should not depend on the detail of the band structure. However, because the insulating peak is always located at half filling, it is not at weak coupling limit either. Because at weak coupling limit, the insulating peak should just follow the Van Hoff singularity position. Finally, we observe two resistance pockets around the half filling insulating peak, where the resistance drops to 0. We suggest that might be subconductivity around the half filling, but there are more experiments to check. So if you are interested in more details, we have a paper come out recently, and I will give a contributed talk on Wednesday. And you can also email me or talk with me in the town hall. Thanks.
Thank you very much, Min-Chi. Our next speaker is Volker de Vries. I shall put a link up on the screen.
Yeah, okay.
And I shall reset the clock. Volker, can you hear me?
Yes.
Please, the floor is yours.
Thank you, Rob. Yeah, my name is Volker de Vries. I'm working in the lab of Thomas Ien and Klaus Enslin at the ETH in Zurich. I would like to present our latest work on density wave states in twisted double bilayer graphene. We're investigating these twisted double bilayers on an angle that's a bit unusual. It's a bit larger than the magic angle. We look at 2.3 degrees. And why we do that is such that we still have some correlation. So the effective mass is still rather high, but also our global top and bottom gate give us control over the two layers. So we do transport measurements, and here on the bottom left you see, let's say, our phase diagram. So we look at Shubnikov-de Haas oscillations, and then we can see what kind of occupation we have in the two layers. And interestingly, we can tune into a regime where one layer or one bilayer is occupied by electrons and the other one by holes. And they're not only occupied by electrons and holes, but also the Fermi surfaces of those are very similar. And therefore, we have very good nesting conditions. So nesting means that the two Fermi surfaces can be connected by a single vector in K-space. And we see the effect of this because we see a gap opening, or we see resistance peak, because these two Fermi surfaces couple and a correlated state or a density wave state emerges. Adam McDonald's group has done some calculations also on the Hartree-Fock approach, and indeed see that this gap opens. And then because we have this great tunability with the top and bottom gate, we look also at what the gap does with displacement fields. That nicely follows the theory, as well as if we take a small density offset between the electron and hole Fermi surfaces. And then we find that such a density offset immediately basically breaks the nesting condition and also destroys the correlated state. If you're interested, please take a look. I will also give a contributed talk on Wednesday, and Elias will also talk about this density wave state in his poster. Thank you.
Thank you very much, Volker. And I apologize for not giving you your clock to speak to, but I thank you for keeping very well to your time in any case. Our next speaker is Gregory. Gregory will, I'll just bring your poster up on screen.
Okay.
And then I'll pass you the floor. So you have 3 minutes. Please tell us why we should come and have a look at your poster.
Okay, thank you. My name is Gregory Polshin. I'm working with Andrea Young at the University of California, Santa Barbara. This poster summarizes our experimental investigation of a new twisted graphene system, which is composed of rotationally misaligned monolayer and Bernal bilayer graphenes. We use double-gated devices, which enables us to change both the total carrier density as well as the displacement field, which is controlling the shape and the isolation of the low energy bands. We find that well-developed correlated states emerge at positive displacement field at conduction band fillings of 1, 2, and 3 electrons per Murray unit cell. While the state at nu equals 2 is a robust trivial insulator, we find that states at nu equal 1 and 3 show quantum anomalous Hall effect with Hall resistance approaching h over 2e squared. This suggests that in these states, electrons occupy a single valley polarized band with Chern number of 2. Moreover, we also observe that the shift of the position of the Hall resistance peaks in small magnetic field also in excellent agreement with Strada formula with Chern number 2. Finally, the value of this Chern number is also consistent with numerical band structure calculations. Besides observing quantum anomalous Hall effect, which has been already reported in TBLG and IBC trilayer, we also discover an interesting new effect at nu equals 3. We find that upon a small Hall doping, the direction of the hysteresis loop switches abruptly. The transition happens without any noticeable suppression of the magnitude of the Hall resistance. This suggests that the transition occurs because the magnetization of each of the two valley polarized states reverses. Another evidence of this is the divergence of the coercive field at the transition. The reversal of the magnetization arises from the contribution due to topological edge states. This magnetization contribution changes linearly with chemical potential inside the gap, and as a result produces a jump in magnetization across the gap. And it was pointed out by Jihan Zhu and Alan McDonald that in orbital Chern insulators, this jump can lead to the reversal of the sign of magnetization. Remarkably, we also find that the magnetic states are metastable and exhibit hysteresis not only as a function of magnetic field, but also as a function of carrier density. And we use this to demonstrate non-volatile electric switching of the magnetic state. Such voltage control of magnetic states can be used to electrically pattern non-volatile magnetic domains, hosting chiral edge states, with potential applications ranging from reconfigurable microwave circuit elements to ultra-low power magnetic memory. Yeah, thank you.
Thank you very much, Gregory. Our next poster is from Jose Angel, and I shall bring the link up into the chat. Reset the timer. And no. And now I shall share my screen again. Jose Angel, you can hear me well?
Yep.
Good, we have you loud and clear as well. Please tell us why we should come and have a look at your poster.
So hello everyone, and thank you for taking the time for coming to the poster pitch session. I am Jose Angel Silva Guillén from the, I think nowadays quite well known, unfortunately, Wuhan University. So during the school, we have seen that although the main twisted material that people are studying nowadays is graphene, there are other families such as transition metal like chalcogenides that also present interesting properties when twisted. In our work, we have done a systematic study of the electronic properties of molybdenum disulfide with varying twist angle using a tight binding model. The main advantage of using this approach to do these calculations in these systems is that we are able to calculate very small angles and even introduce spin-orbit coupling in the calculations, which in this material it is known to be quite important. One of our main findings is that for small angles, larger than in the case of graphene, we already see flat bands. these flat bands become narrower as we decrease the twist angle. Also, the band gap of the system follows the same behavior. If we plot the local density of states, which I do not show in the poster, we see that the states of the flat bands are localized around one of the 4 types of high symmetry stackings that appear in the Moirier cell. An interesting thing happens when applying a spin orbit coupling to the calculations. We find that it has a very little effect on the valence band. On the other hand, looking at the conduction band, we find a spin orbit splitting at the K point. This is quite surprising since at K, a large splitting is not expected due to this effect. We think that this is due to the fact that the so-called Q point that has a finite contribution of the px and py orbitals of the sulfur atom falls to the K point of the mini-brilliant zone of the twisted sample, while in the valence band, we only have D0 and Pz orbitals. It is also important to mention that the spins at the edge of the conduction band at K and K prime are opposite. And just to wrap up, in the 2 papers that you can find in the reference section of the poster, we also study how the electronic properties of the system are modified when applying pressure, electric field, etc. So if any of you are interested, you can look at them, talk to me later or send me an email. Thank you.
Thank you very much, Jose Angel. Our next speaker is Kevin Knuckles. The link to the poster is here. And if you give me 1 minute, I'll bring up the poster on the screen. Kevin, can you hear me?
Yeah, can you hear me?
Yes, I can, loud and clear.
Fantastic.
Your poster's up on the screen. You have 3 minutes to tell us why we should come and have a look at it.
Thanks, Rob. So hi, everyone. My name is Kevin Knuckles. I'm a graduate student at Princeton University in Ali Yazdani's lab. And today I'm super excited to tell you about our new results that were published in Nature last month, exploring the high temperature parent phase of magic angle twisted bilayer graphene. So, you know, this platform has a really complex, rich phase diagram, largely due to the, I guess, many physical manifestations of strong correlations in a topological flat band. It's a really unique setting, and it's further enriched by the fact that this system has an internal intrinsic quantum degeneracy. We get the spin and valley degrees of freedom from the graphene layers themselves. And so a really fundamental question that we wanted to probe with STM was how these 2 paradigms of strong correlations and the intrinsic quantum degeneracy, how those 2 interact with each other to produce such a vibrant phase diagram. And so the main result is that we uncover with you know, the spectroscopic and spatial capabilities of STM a high temperature, very correlated parent phase from which essentially the low temperature, more fragile ground state phases emerge. So the way that we do this is we see in spectroscopy on an AA site in magic angle graphene, we find that as the filling is tuned in the system, we can tune the flat bands to the Fermi level. In the middle of my poster, you can see that those flat bands undergo a series of splittings into what we're calling Hubbard subbands. These are bands of states that arise from the broken flavor occupancy degeneracy due to electron-electron interactions. And we know this because we can see from a very simple theoretical model using a Hubbard repulsion U that's on site that we can reproduce very much the same features in spectroscopy as we do in a very simple model. So, and in addition, we can probe other states in the system. We can probe remote band states as we're filling the flat bands. And we find that this is a good proxy for the chemical potential of the system, which is really new. It's a nice insight into the system that undergoes a number of chemical potential resettings at integer fillings. So these are all characteristics of the parent phase of magic angle graphene, and I'd be happy to speak to people about this at the online town. I'd be happy to talk to people in transport who are can see many parallels between our data and their data. And then finally, we have this new paper up on arXiv as of last week, where we employ a novel technique using millikelvin STM to discover a sequence of churn insulators in MATPG in the absence of HBN alignment. So the spectroscopy methods that we have can really tell us that these are correlation-driven churn insulators. And although my poster is not on this, I'd be happy to talk to people about this as well. So thank you.
Thank you very much, Kevin. Our next poster is by Pierre Anthony. Pierre, can you hear me well?
Yeah, I can hear you.
Good. The link to the poster is now up on the chat. I'll bring the poster up on the screen. And you have 3 minutes. Please, the floor is yours.
Okay, thank you. Welcome, everybody. My name is Pierre Pantaleon. I am a postdoctoral researcher in the nanoscience, and this poster is about the flat bands in graphene stacks. Let's start with the pictures, with the drawings. If we have a graphene over hexagonal boron anhydride, the graphene fills the potential due to the substrate. So the question is, what happens if we introduce more and more graphene layers over the hexagonal boron anhydride? So in the recent years, had been reported some correlated states in these systems. So the question is, in this system, are they different? The flat bands in these systems are different than those in twisted bilayer graphene. That's the main question that we are trying to solve in this poster. So the model is very simple. We have the graphene, we have a potential induced by the substrate. We introduce a self-consistent Hartree interaction, and we analyze the presence of the narrow bands in this system. After analyzing the existence of the narrow bands in this system, we introduce a Hartree potential, and we study how are they changing as a function, for example, of the filling. So we found that, in fact, for these systems, the distortions of the bands are quite smaller than in twisted bilayer graphene. This means that the correlated effects that have been observed in these systems are probably of different nature. For example, if you see my poster in detail, I show some band structure as a function of the filling for bilayer graphene over HBN, trilayer graphene over HBN, and twisted double bilayer graphene, where you can see that the band distortions are small, even with a small dielectric constant. So the question here is still open. What is the nature of these correlated states in these systems? Are they, how far is the difference between the correlated states in this system and twisted bilayer graphene? So if you visit my poster, you can see some beautiful pictures, and obviously the effect of the Hartree interaction in this kind of systems. Thank you.
Thank you very much, Pierre. Next, and our penultimate speaker is Hector. I apologize if I pronounce your name incorrectly. I'm not sure which one I should use. You can correct me when you introduce yourself. The link to the poster is on the chat. The poster can be seen here on the website. And you have 3 minutes. Please tell us why we should come and have a look at your poster.
Okay, thank you. Hi, everybody. My name is Hector Ochoa. I'm from Columbia University. So the motivation for this work was to understand how the conditions of the samples, and more specifically the presence of a strain, favors different forms of symmetry breaking close to the neutrality point. So we all know that twisted bilayer graphene is a multi-scale system with many internal degrees of freedom of orbital origin. And it's not obvious a priori how Coulomb interactions leave these degeneracies close to the magic angle and particularly close to the neutrality point. So this is, for example, manifested in the variety of possible ground state solutions of different symmetry that you find, for example, in Hartree-Fock calculations, as Lenny mentioned, for example, this morning, and we have several talks about it last week. But more importantly, this is also manifested in the experiments, in particular in transport, where some devices are insulating around the neutrality points, and others are not. So in my poster, I discussed the effect of a strain accumulated between the layers. This sometimes called heterostrain. So these strains are widespread in twisted bilayer graphene, basically due to the fact that the samples are only metastable. and are usually manifested as variations of the Moiré period across the samples. For example, in STN, we saw some images in Eva and Dreysto this morning. So the effect of heterostrain on the low energy bands is illustrated in the first panel here. So basically, strains shift the Dirac points in energy. Here, blue and red represent the two valley flavors, which has to be inverted due to time reversal symmetry in the opposite corner of the Moiré Briançon. But the important observation is that the resulting Fermi surface close to the neutrality point is generically unstable relative to the condensation of electron-hole pairs due to the overlap of the conduction and valence bands in such a way that an excitonic gap is opening in the electronic spectrum. So this tendency towards electron-hole pairing involves correlations between these internal degrees of freedom. The matrix structure of the other parameter in sublattice and layers are basically predetermined by the approximate electron-hole symmetry of the continuum models, but these are arbitrary in value, so at least in this continuum theory. So that means that we have a manifold of states parameterized by the pairing phase, which physically corresponds to different patterns of circulating currents between the layers that give rise to an orbital magnetization density wave with a Kekulé-like pattern on the atomic scale. So actually, the different pairing symmetries or the different pairing phases parameterize patterns of different symmetry. And this is just like in the so-called parameters intervallic coherent state that we hear about last week in the talk by Adrian Bismarck. So the main message is that the most homogeneous samples, which are display insulating behavior at low temperatures close to the neutrality point, are most likely the result of uniform strain fields that stabilize the relative alignment between the layers, and therefore favoring this excitonic instability and this intervallic coherent state that I mentioned. But this state is very sensitive to disorder and deviation from these uniform strain profiles due to the loss of electron-hole nesting, so which is has a pairing, pair breaking effect acting to magnetic on the superconductors. So that's basically all. Unfortunately, I cannot join to the this chat thing. I will do it tomorrow, but if you have a question, just shoot me an email. So my address is in the poster. Thank you.
Thank you very much, Hector. So we have one more poster for today. And our last poster is from Elias. I'll give you the link now in the chat.
Okay.
Elias, can you hear me?
Yes, I do. Can you?
Yes, I hear you well. So here is your poster, and please, the floor is yours.
So my name is Elias Portoles, and I'm a first-year PhD student in the group of Thomasin and Klaus Enslin. And the device I'm going to talk about is actually the same in which the experiments presented previously by Volker de Vriest were performed. So we have a system of a twisted double bilayer graphene at 2.37 degrees. So it's this intermediate angle. I'm going to start talking straightforward with the upper right box. So as a reminder, we have a correlated state when we tune our gates in a particular electrostatic configuration, and in which the electrons, the electrons of same spin couple to enter this correlated state. Then, as is seen in the picture, if we apply some Zeeman field, we can shift the gaps corresponding to each spin polarization, and then by tuning the Fermi energy, we can choose which spin is the one that forms our correlated state, therefore polarizing the rest of the electrons, which means those that participate into the transport. Now, knowing that, we engineer an inner-outer region configuration, which is shown in the schematics of the next box, in which, so first we apply again a Zeeman field, and then using local top gates and a global back gate, we polarize differently the inner and outer regions of our device. We make a current flow through all these regions, and then we measure its resistance. Now the results are shown in the last box, the spin junction box. So in our experimental results are shown in the right, and the schematic in the left explains basically this data. So what we see in the X and Y axis is the polarization of the inner and outer region, green for the inner, red for the outer. And what we want to look at are these gray boxes. So those configurations are the ones in which there's a spin up polarization in the outer region and a spin down in the inner region, or vice versa. Now what we see is the increasing resistance from the unpolarized regime to the oppositely single spin polarized regime is higher than the sum of the resistance increase of only polarizing one of the two regions. So as you see, if I do the sum of delta R2 and delta R1, which correspond to polarizing only the outer or only the inner region, I have a resistivity increase of around 4 kilo ohms. While if I oppositely polarize both of the regions, I have an even bigger resistance of around 5 kilo ohms. So it's a 20% difference. And that it's not a, we cannot take any conclusion from this, but that leads to some spin valve behavior in our device. And that's all basically for this part of the poster.
Fantastic. Thank you very much, Elias. So thank you to all of our speakers today for presenting your posters. Most of the speakers will be there in Online Town, so I encourage everyone to join Online Town to talk to them and to talk to the speakers from last week and from this week who will join. Some of them will join also in the discussion. For those of you who joined the discussion today a little bit late, I'm also going to repost now in the chat of the Zoom meeting a link to a YouTube channel where we've posted videos from the seminars that were given last week, and we will post also the seminars that were given, that being given this week as they are ready. So please, I encourage you to have a look at those videos, to rewatch the talks you've seen or to watch the talks that you missed, and to reach out also to the speakers from all of our seminars, and to come and ask questions in the Online Town sessions that we have today, tomorrow, and on Wednesday. So I look forward very much to seeing you in Online Town, and I invite you to come back tomorrow afternoon, 3 p.m. Barcelona time, whether that's in the morning or the evening, depending on where you are around the world, for our next talks. The next talk tomorrow at 3 p.m. will be from Atachi Mamoglu from ETH Zurich. And we have a talk also from Rafael Fernandez from the University of Minnesota tomorrow afternoon, as well as another one of these poster sessions. Thank you all for joining us this afternoon, and I look forward to seeing you in Online Town. And thank you again to all of our speakers.
Thank you.
Thank you.
Okay, thank you very much. Thank you all. And I'm gonna end this meeting. I'll see you in the Online Town. Bye-bye.